Hello, welcome to another Stat385 video. In this video, we're going to talk about functions. We've talked about functions before, so more specifically, I'm going to sort of talk about miscellaneous topics related to using and writing functions that sort of didn't fit in anywhere else, but I want to make sure that you are aware of or have at least seen once. So these will be things that maybe aren't as foundational as sort of previous discussion of functions, but nonetheless, they are all things that you are likely to either directly encounter at some point or is sort of silently happening and you don't even realize it. So by being able to put names to these concepts, I think it'll help you better think about the R code that you're both reading and writing. Okay, so first, I want to talk about function composition. And what I really mean by that is sort of, in mathematics, if you have a function f and a function g, you could compose them together by doing f of g of x. So, put as input to the g function x, and then take the output of the g function and immediately pass it to the input of the f function, right? So that's the kind of thing you've seen in math all the time. You maybe remember like, how do you take the derivative of functions that are composed like this? And there's rules to all that, right? But okay, so we want to think about that with respect to writing code in R. So, for example, we could think about something like this. So we have, let's create a vector x with some values in it, nothing we haven't seen before. And now let's do the following. Let's take the mean of the log of x squared. Okay, so what we've ultimately done here is some function composition. Let's just make this more ridiculous just for the sake of doing it. So this is kind of weird too, because realistically, this is a function this is a function with arguments x and squared. And then the output of this is immediately passed to log, is then passed to mean, is then passed to square root. Okay, well, you might say, I don't know, that's not super easy to read. I mean, frankly, this example is not too terrible to read, but you can see how if you just constantly make the output of one function the input to the next, it becomes difficult to sort of see what's going on. So another way we could do this is store is kind of the wrong word, but give a name to the intermediate objects created. So I'm going to be lazy and do something like this. And then so the next is log of the previous, and then, and then out is now the mean of that, and then lastly the square root of that. Okay, so I'm going to rerun this, and now I'm going to run these, and we get the same thing, right? So this is a technique you will end up using. There's kind of, I don't want to say there's no way around it, but at the end of the day, sometimes storing an intermediate result is useful. Now, the downside to that is that you have to assign all these names. And I'm even being lazy, and I do like to promote being lazy, but here I'm being lazy in a bad way where I am reusing a name because I was too lazy to think of a good intermediate name for each of these things. Like I don't want to. Naming things is hard, and I didn't feel like doing it. Okay, so this is another way to do it, but don't really like it, right? So another way to do this would be with something called the pipe operator. So I'm kind of regretting my choice of functions here, but I think I can get around it. So, okay, so I'm going to cheat a little bit and run this first, and now I'm going to put parentheses around this just to be safe. Okay, so now I'm going to use this symbol here, and let's see if I can just kind of make this work for myself. Okay, what was next? Mean, and then square root. Okay. Same answer. So what happened here? So here I kind of cheated a little bit and did my first function, and then I took the output of this, and we'll say piped it or sent it to this function. So whatever the output is here is now the first argument to this function, log. And then I take the output of that one and pipe it to mean. And whatever the output of this is the first argument to mean, and so on and so forth. So this would be called piping. You can kind of see how it does exactly what this does, but in a certain way, some folks will find this syntax just easier to understand and read as a human. And that can be sort of a personal preference thing. So a couple things here. So this operator right here called the pipe is very, very, very new. It's within the last year in R. And this is, I'm not using any external packages to load in this pipe. Now, later we're going to see this symbol, which is also a piping operator, but this comes from an external package. So I actually couldn't use this right now because this function is not loaded. But you're going to, as the landscape of R stands right now, you're going to see this a lot more often than this. And I don't know which way that's going to break in the long run. So I'm showing you this right now just to show you sort of the three different compositional styles. But know that this one, later we're going to use this one instead for pipes, and I'll explain that later. But just know that these are both symbols you're liable to see in the future. Now, for me personally, I kind of like a mix of these things, and it really just depends on the exact sort of function I'm writing, the exact code I'm writing, and how I'm feeling at sort of any given moment. But I want you to be aware of all these styles. We're gonna heavily leverage this one later on, because when we introduce something called dplyr, I would sort of argue that's sort of the de facto way that people write that code. So we're gonna lean into that. But for myself personally, I would say I use a mix of the three, and it's highly situationally dependent, and I don't have a good heuristic for you. Right. I'm trying to decide if I want to elaborate on that further. I think I did another example in class, but I don't think it was all that useful. So yeah, so those are the sort of three sort of ways to compose functions. That is, run functions on functions on functions, which is something, because everything you do in R is a function call. So it's one of those things, like it's kind of like simultaneously so obvious, but when you give a name to it and you show these different styles, it'll subtly affect the way you think about code. So basically what I would say is, if you start seeing something like this and it's super, super long, and like all the different functions have like multiple different arguments passed to it, you're going to want to do some combination of these two things to alleviate that a little bit. But we'll see code like that later. Okay, so something we haven't talked about at all is scope. So pretty much, I think, up until this moment, anytime we've written a function, all of the things that we use within the function are defined within the function. And frankly, I'm just going to suggest that that is a good way to do things and a good heuristic. So only use the arguments of the function and other things that you define within the function. Don't pull from the environment outside the function. The other thing I'm going to mention here is that we're going to just like very briefly mention the idea of scope, but the rules around it are long and a little bit complicated. See the reading if you're interested in that. And it also relates to environments, which are something that we've kind of tiptoed around, and we're going to continue to tiptoe around, because I view that as sort of outside the scope of this course. But what do I mean by this? Okay, so if I run this function, it works just fine. Okay, great. But what if I did something like this? Well, now it errors because, well, it knows what x is because we're supplying it as an argument, but it has no idea what y is, right? It has no clue. So now what I'm going to do is so right now there's no y in my environment. So what I'm going to do is I'm going to supply y as 5. So now when I run f of 4, I believe the end result is going to be 16 plus 25. Don't ask me what that is. I'm bad at arithmetic. 41. I believe that. Okay. So what happened here? So inside this function, when we ran this code ran. Now, what does it use for the value of x? Well, we explicitly told it by passing that as an argument. We can make that even clearer by doing something like this. Okay, great. But then where did y come from? Well, there's no y as an argument to the function. So what it does is it then looks outside the function, in this case in our global environment, and sees, oh, well, there's a y there, so we'll use that. Okay, so to be even clearer, we couldn't do something like this because we didn't write that as an argument. More on that in a second. The other thing that might be interesting to note here is let's now define x in our global environment, and we'll make it huge. So x is 10,000, y is 5. But note, if I were to try to do this, that doesn't work because there's an x argument and there's no default, so it has to be specified. But if I do this now, it still returns 41 because within this function, it's going to use for x this x that's an argument, but it's going to find y outside of the function because y is not an argument to the function. Okay, so I mentioned this because you'll probably inevitably accidentally run into this causing you an issue. So what'll generally happen is you'll probably be coding away and sort of you'll be on a roll and you'll write a bunch of code, but somewhere you'll have defined something in your global environment and then used it inside of a function without making an argument. And then this global environment will go away and you'll load up the code the next time and now it won't work because you used a name in the scope of your function that was not ever passed to your function because it's not an argument to the function and it doesn't exist in your global environment. So that's kind of the issue there. Okay, so that's a tiny little bit about scope. Lazy evaluation. So lazy evaluation is kind of a detailed topic, but let's look at another function g. And let's do this. Okay, so if we go back to our f function, right, and I say f of 4, that runs, okay, because, and then specifically what we're saying is, because it's the only argument, so we're supplying 4 to x. If I try to do something like this, that doesn't work. Can't do that because there is no y as the argument to the function. Okay. The other thing we can't do is we can't fail to supply x. And both of this error and this error, don't read too much into them because this is not necessarily what I would call normal behavior. It's an instance of a specific behavior, and if you try to extrapolate from these two too much, you're gonna learn how R functions incorrectly. So what are the issues here? So let's look at this g function, right? So based on this right here, you might think to yourself, oh, well, if x has an argument, I have to specify it. No. So let's do this. Why does that work? Because clearly the g function has a y argument. So why don't I have to supply it? The issue there is lazy evaluation. So much in the same way that we want to be lazy when it suits us and it makes our life better and easier, so does R. So what R is doing here is it's saying, well, I'm going to start running the code inside this function. And when I do, I'll then go back and reference the arguments to check for if the value is there. And if it's not, then I'll go look up in the global environment. And if it's not there, I'll run into a problem. But so it doesn't evaluate the arguments when you run the function. It evaluates the function when the code inside of it is run. So because this y is not used in the code here and is never run, it doesn't care. So you can get away without specifying it because it never actually evaluates the value passed to y, even though it's not there. Okay, so that's something that won't come up all that often. The one, and I should have thought of an example that would trigger this, but so occasionally when you create an object in the environment here, you might not see a value. Instead, you'll see a promise. And without getting into the details of it, it's part of the whole lazy evaluation mechanics of R, such that, well, you told R to create the object, but it's going to be lazy and not actually do that computation until you reference that object somewhere else and actually use it. So I can't think of an instance where that's going to happen inside of RStudio, but occasionally you'll see promise written here. Don't freak out if that happens. That's normal. That's because R is being lazy. It'll do the computation if you truly need it later, but it's going to try to be lazy in the meantime. Okay, so maybe more important than that is this notion of dots, right? Okay, so we saw how the f function has this x argument, and if I tried to run it without supplying x, it says, well, no. Actually, wait, that's not the example I wanted. I want to go back to, sorry, let's write a new function h. And sorry, that's not the example I wanted. Let's do this. Okay. Like that. So h just puts out its argument. Okay. So if I try to do something like this, if I try to do h, x is 9 and y is 10, it's going to yell at me because it's going to say, hey, there's no argument y to this function, so you're doing something wrong. And that's true in this case. However, don't try to rely on this behavior. Watch as I do the following. So I'm going to run the mean function on the values 1 through 10, but I'm going to supply an additional argument. And the name of this argument is going to be based on me randomly typing things. So it's going to look like that. It's literally nonsense. And then I'm going to give it the value 10,000. And that code runs. I am absolutely positive, without looking into it, that this is not the argument name to any function in R, let alone the mean function. So why am I allowed to supply it when for this h function, R very quickly says, no, 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 no. Y is not an argument to the h function. What is going on here? What's happening is the mean function, like many functions in R, uses the dots argument. So if we look at mean, well, first we see that it's a generic function. That's confusing, and we'll explain that in the next video on the S3 system. But if we look at the usage, it takes two arguments, x and dot, dot, dot. So basically, again, we're not going to go into the nitty-gritty details. We're just going to look into some basic usage. When a function has dot, 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 that allows you to take in not just the arguments that it needs, like this x, for example, but additional arguments that then might be passed to another function. So let's maybe write an example of this. I should have prepared a better example. Okay, so this h function, I'm going to allow to take in dots. I need another function. Well, okay, so do I want to use mean here? No, I want to write my own. So let's write two functions. Okay, so let's do x squared plus y squared plus z squared square root of that. Okay. And then the h function is going to do, let's do 2 times g of dot dot dot. Okay. Oh gosh. Okay, so this is not the best example in the world, but I think it's going to be clearer than if I use a built-in function. Okay, so we can run the g function as you would expect. Cool. But so the h function has an x argument and then dot dot dot. Really, I didn't need to break out x, but I'm going to regret. Let's do this. Let's make this XYZ. Let's make this A, and let's make it A times that. Okay, that should be clear. Okay, great. Okay, so here I'm going to supply A is, I don't know, 10. So we'll get 10 times this result if I pass the same values. And when I run this, it doesn't work because we're trying to run this g function, but g requires x, y, z. Okay, so this h function, we're going to need to give it more arguments. And in particular, we're going to need to give it x and y and z. And now it works, and I think it should be 10 times this value. So what's happening here? So a is 10, and that's here. But then all these other arguments that aren't actually named arguments to h get sort of swept up in this dot 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 thing. And then by passing the dot 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 to the g function, all of these arguments are then passed to the g function, which then satisfy this here. So that's kind of how dots work. But that's why, you'll see them all the time in all these R functions. And that's so you can pass on, when you're using a function that perhaps uses another function within it, you can keep passing arguments down into those nested functions. But that comes at the cost of you will not get errors like this when you do things like this. And where this will sort of bite you the most, unfortunately, is with autocompletes. And this is a technical problem that I don't know how anyone would solve this. But so if I try to do mean, okay, so I can do this, but, oh, that's interesting. Never mind. Huh. Maybe RStudio recently improved this and I'm operating on like a 3-month-old thing. So I could be wrong about this, but sometimes when you have a generic function like this, and again, that's not quite understandable because we haven't talked about S3. If you have a generic function and dots, it will not autocomplete the arguments for a specific method, and then you might have to type it manually and you'll mistype it and it'll be wrong and it won't do a thing because it will accept the argument, but it won't be passed to the argument of the same name and things will go wrong. But now I don't have an example of that because I feel like RStudio is being smarter than me and I don't know how to create one right now. So, but that's why I mentioned that. So there's that. Okay, so that's a little bit about dots. We'll probably do an extended example in a lab that shows the usage of those better, but that's a general idea. Okay, so I want to talk about, I can't remember if I've done this in a video or not, but I did it in class briefly, so I need to make sure I put it in a video. Functions can be run using multiple different forms. So for example, a prefix function is something like this. So where you write the function name, then open parenthesis, and then pass in the arguments like such. Okay, so that's the one you're most, probably most familiar with. When you think function, you probably think prefix form. So infix is something like this, where you have an operator like this that takes an argument on either side, hence infix. sort of like in between. So the arguments are around the operator, and then the function is run as such. Now, I would note that you can always take an infix operator and turn it into a prefix form. So what I could do is, so it's something kind of like this, but because this is not a syntactical name, we have to surround it in backticks. And now this will do the same as this. Technically, I think it's safe to say that all functions can be written in prefix form, but I'm not going to do that for the other two because it's trickier and it's not that important. Okay. So another type of function that we've seen is this notion of a replacement function. And these are a little weird, but so for example, if you do something like, so we have X is this thing here, I guess, but if I do names of X, some name, not note, name, and I look at X, now it has a name. So technically we're writing a we're running a function here, but what it does is it replaces something having to do with X, in particular here, the name attribute. I don't want to belabor this point, but this is running a function and it's doing a replacement, which is kind of weird to think about given how all our other functions work, but this is something that exists. If you want to see either how to write these yourself, or if you want to see how to change them into a prefix form, have a look at the relevant chapter that I linked from Advanced R. Special functions, there are kind of a bunch of them, but examples that we've seen are for is a special function. Brackets, not P, brackets are also, well, generally we refer to just the first bracket or something like this, except it's doing autocomplete for me. So these are all special functions. They're special because they kind of don't fall into any of those other three categories, I think, for lack of better explanation. But I mentioned this just because I think sometimes when you look at code, when you see a prefix form, you go, I'm running a function. But when you see infix, you might think to yourself, oh, I'm running a function. But when you're doing these things, sometimes you might go, oh, wait, that's a function? And it is. And again, I think if you really want to understand these two, again, in Advanced R, it both shows you how to, turn these into prefix form, which I think will maybe better illustrate to you how they are indeed functions. But just something to be aware of, because as much as I say everything we do in R is a function call, sometimes that's not as clear if you don't realize that all these different things are technically running a function. Okay, so one last thing is I want to talk about signaling and handling of conditions. So conditions I'm going to limit to messages, warnings, and errors. I think there might be technically other conditions, but those are the three, well, we have seen and you will continue to see. So messages can be signaled with the message function. This is a message, and it, in this case, inside of RStudio, it'll make red text that is often scary. But so a message is literally nothing but information to the user. It's not a warning. It's not telling them there's something wrong. It's not an error. It doesn't stop the code from running. It's just a message. It's informational. And the situations that you would use those in this class, probably not going to use it. So a warning is triggered with warning, and you say this is a warning. So this also triggers red text in RStudio. It might be a different color if you're running this on the command line, but that's not super important. But it's also preceded by this warning message telling you that it's a warning. What is a warning? Well, we've seen this one a bunch. So a warning generally occurs where your code runs, but it likely had an unintended consequence. From my perspective, especially as a beginner, I would just advise against using warnings. You should be aware of them because you're going to see them based on code you're running and creating, but I would not, as a beginner, put any into your code. What I would instead do is errors. If something is being used in a way you didn't intend it to be used, just throw an error and make your user deal with it. That's kind of a heavy-handed approach, and there are subtleties there that you should probably at some point consider. But as a beginner, just throw an error. Don't let your user do crazy things. How do you throw an error? The stop function, kind of breaking thing. This is an error. And when we run it, we get error. This is an error. Okay. So we'll need to look at sort of a better example of this. So let's consider a really silly function, square. Let's call it square. And it's going to square the x variable. Okay, cool. So if I do square 1.1, squares that number, no problem. If I do square true, it returns 1. If I do square a, it says non-numeric argument to binary operator, and it shows me roughly the code that caused it. Okay, so what we could do as the author of this function is try to help out our users a little bit and to simultaneously do a couple things. Basically, don't allow this and simultaneously don't allow this. So there's kind of a couple different approaches here. So there's another function that's related to stop called stop if not. And what this does is it will trigger an error through stop if a certain condition is not met. So in this case, if I say is.numeric x, so it's going to check is x numeric. And if it's not, it's going to throw an error. So let's try that. So that works. That doesn't. And that doesn't. Great. Now, I would argue that maybe this message is still not the best. And actually, I forget about something. Yeah, anyway. Okay, so also here we're getting some hints that RStudio would allow us to do some, what do you call it? Debugging. It sort of shows, okay, so here's the code that I ran. Then here's the line of code that led to the, so this started leading to the error. This part of the code led to the error that we never even got here. And then this code triggered this code, which is what actually made the error. We'll maybe come back and talk about debugging later, but that's something that you'll see occasionally is this traceback will help you see that kind of thing. Actually, I was curious about something. Okay, anyway. So the other thing we could do, instead of stop if not, we could do the following. So if not is dot numeric x, stop x must be a numeric vector. Okay, so now this works. This throws an error and it says x must be a numeric vector, which is to a user much more useful because when we saw, for example, this initial error here, when we didn't do any signaling of conditions ourselves, it says non-numeric argument to binary operator. But your user of this function, Square, they don't know what's happening inside of it unless they look at that themselves, but they do know that they need to supply x. So like it's not hard to see what's happening here in this case, but that's because it's a very simple function. But directly telling them, well, x must be numeric. Well, they know I input x, so that makes sense to me. And then one thing you can sometimes do here, because this part's not quite necessary when you have a nice message like this, you could actually turn off the call. So what I mean by that is now it's not telling you where the offending code was because that doesn't really matter because it's very simply your input x needs to be numeric, and it's not. Okay, so there's that. Okay. Yeah, but so you can see how this is maybe, it requires more to write it, but stop if not is sort of a helper that helps you do that a lot faster, although it's not as verbose, at least not out of the box. There might be a way to modify that, but I haven't thought about that recently. Okay, so another thing you might want to do is handle conditions. So I'm only going to show you one way to do that. There's a ton of ways to do that. I probably should have linked the reading from Advanced R about this. If you're interested, you can find that. It's pretty easy, but I don't want you to get bogged down in this. Before I go on, I should say that now that I've shown you this, you might, what's the word for this? I don't want you to overreact. And by that I mean, so far in this class, you have never wrote code like this. That is, you've never written code that verifies that the arguments to a function take in objects that we sort of describe that we want, right? So in every PrairieLearn quiz, where we had to write a function, we say, okay, so write the function, give it this name, and give it these arguments. And then we sort of give you a description of all the arguments with respect to the types of objects we expect them to be. So you could then always write code like this that throws an error if that object is not of the correct type, length, whatever we specify about that object that you want to worry about. Don't do that. So what I want to say here is, unless we tell you you need to be doing this kind of thing, assume you don't have to be. So there's kind of an art to how defensive do you have to be in your programming. So basically what this is doing is you're guarding against your user doing something that they shouldn't. But that's in some sense, I don't want to call it an advanced thing, but like I'm guessing that most of the code you're writing right now is for us in the class to verify that you know what you're doing, and maybe for your own internal use. So with that in mind, spending a ton of time doing this is not going to pay a lot of dividends. Now, that said, if you're writing a package that's going to be used by a lot of people, well, then the need to become defensive ratchets up very quickly, and you need to be considerate of that. So, but there's trade-offs there, but basically, I don't want you to drive yourself crazy. So unless we say otherwise, when we say, hey, write a function, and the argument x should be a numeric vector of length 1, you can rest assured that we're only going to test your code on numeric vectors of length 1. You don't need to check that we have input a numeric vector of length 1. That is until we write questions where we check that you can do this sorts of thing, in which case we will directly ask you to do that. Okay, so a little bit about handling conditions. So sometimes you might encounter something where, let's say we wanted to do something, I really don't even, now that I'm thinking about this, I want to show you this. But so you could encounter a situation where you need to run code, but it might create an error, but you still want to run the code after that error would have happened. And there's a number of ways to do this, but a very common one is something called try catch. So basically what's going to happen here is, let's try to run this. So this will just run. But then let's try to run this. And it's going to error. And that's expected. And seemingly this try catch has done nothing for us. But what we want to do now is, there's an argument to this function called error. And it expects a function. I'm going to put condition here. And basically what's going to happen is, if this triggers an error, this function is then going to run and then it's going to return whatever this is. So let's try that now. So now when we run this whole thing, it returns NA instead of erroring. And sort of where that could be useful is if you need, actually, can we do this? No, I can't. It would be, I'd have to come up with a convoluted example. But so I recently, I have some code that's written up in a function, and I'm basically taking that code and running it with a bunch of different inputs. But for like a really small percentage of those inputs, it triggers an error for reasons that I'm just for simultaneously don't want to and too lazy to go fix in my code. So instead I want it to return an error. So by putting this try catch around it, I have all the results for when it does an error and then NAs for when it does it. And then I can like operate on that vector and my code didn't stop. So that's the deal. And then also whatever you name this, you could use inside of here. So if we run this now, so this function is being run on the error condition, that hence it's a handler, and I can actually operate on that condition and it shows me the condition, but don't think too much about that. If you're interested in that kind of thing, read the relevant chapter in Advanced R, but one of the more common uses of this is going to be something like, well, if I encounter an error, return something like an NA, so I'm realizing that for that sequence of inputs, it errored, but I can go on with my code with other ones. Okay, so that might have been a little bit all over the place, but hopefully you picked up on a couple things here and there. Yeah, so these are all things that I wouldn't expect you to have a deep understanding of, but I all think that having just even just an awareness of them can make things that you're going to see and experience when coding R less mysterious and frightening, and you'll just have even the vocabulary to know how to go search for what's happening in a reference text or on Stack Overflow or something, rather than it just being a pure mystery. Sort of dots being one of the more important things, because you'll see so many functions have a dots argument, and that is something that's used a lot. Okay, so as always, if you made it to the end of the video, good job.